Hello everyone, welcome back to another video. In this video, I'm going to continue my Kerbal Space Program series. If you were following along, in the last video, I went to Ike and back, but I left Bill Kerman in space. So currently, he's in solar orbit right now. And in this video, I'm going to try to rescue Bill Kerman uh, so that we can go back to Kerbin. So, without further ado, I guess let's get to it. Now, the problem here is that Bill Kerman is not a planet, right? So, usually, when we do interplanetary transfers, we go to the internet and find a transfer window diagram, and then we time warp such that the planets, such that the Kerbin and the target planet is aligned at a specific angle so that it takes the least amount of delta V to go to the target planet using a Hohmann transfer orbit, right? However, Bill Kerman is not a planet, right? And his orbit does not match any of the planets except for Kerbin. So I can't just Google and go to the internet to find a diagram for the optimal transfer window that I need to use to launch from Kerbin to get to Bill Kerman. So instead, what I'm going to do in this episode is I'm going to calculate it, right? Because on the internet, I found this article by NASA, which basically lets students calculate the next optimal transfer window from Earth to Mars using the Hohmann transfer orbit. But I'm going to appropriate this so that we can instead rescue Bill Kerman from being stuck in outer space. So let's get to it. So let's go down. So yeah, we're basically wanting to calculate when should the spacecraft launch from Kerbin to get to Bill Kerman. Right. So like what difference in angle between Bill Kerman's position relative to the sun and Kerbin's position relative to the sun, right? So that we can launch optimally, right? So here in this diagram, the optimal sort of angle difference between Earth and Mars is like this much, right? So less than what? How many degrees is this? It looks to be about like I don't know, 60 degrees. Right, so let me go down here. Yeah, so this article calculated that the position of Mars at the time of launch relative to Earth is 44 degrees ahead of Earth, right? So here, we can conclude that a launch opportunity occurs when Mars is 44 degrees ahead of Earth in its orbit, right? Now I'm gonna try to calculate in this episode the launch opportunity for Bill Kerman, right? Right. So yeah, let's do that. So yeah, so first of all, let me go through the points here because this is a step-by-step guide for students. Okay, so procedures, blah blah blah, explain what a Hohmann transfer is. I don't think I need to explain that in this video. So I guess first of all, the article wants to have the student draw the orbits of Mars and Earth, right, around the sun. Or in this case, Bill and Kerbin. So I already did that, right, off camera before recording. So this diagram which I've prepared, we have got the sun or Kerbal, we got Kerbin, and then we got Bill Kerman right here. So yeah, I included here in this diagram the distance from the center of the sun to the center of Kerbin and the distance between the center of the sun and Bill Kerman. This number might not be accurate, but let's just roll with it because I don't want to correct it because I don't want to waste further time. So the first step is drawing the transfer orbit. So let's just do that. Okay, let's just pretend this is the the Hohmann transfer orbit from Kerbin to Bill Kerman. In the Hohmann transfer orbit, the actual path that the spacecraft will take to get from object A to object B is half of the Hohmann transfer orbit, right? So let me just... There. Yeah, that's definitely high quality. Okay, as you may notice, I've put in here the distances both in kilometers and in KU. Now, what is KU? KU stands for Kerbin unit, and I kind of made it up. And it basically just represents the distance between Kerbin and the sun, right? So Kerbin's distance from the sun, right, in its orbit is 1 KU. So 13.6 million kilometers is 1 KU for the purposes of this video, right? And then I just put the distance from Bill Kerman to the sun in Kerbin units as well. So, what is the next step? Have students use Kepler's third law, the law of harmony, to determine the period of the Hohmann transfer orbit and then the travel time to Mars along this orbit. So travel time to Bill Kerman, right? So Kepler's third law states that the square of any period of the period of any planet is proportional to the cube of the semi-major axis of its orbit. An equation can represent this relationship. So p squared is equal to k times a cubed, with k being the constant of proportionality, which this article assumes is 1. Using Kerbin as an example, we can measure p in Kerbin years and a in Kerbin units, right? Okay, so in this example, they use Earth, right? So Earth years and Earth astronomical units. So 1 year, so p, okay, great. So this is what we need to do, right? So how do you do that? So let's do p, let's just say is 1 Kerbin year. Yeah, let's say a is equal to 1 KU, right? Just put a comma here. All right, so now p squared is equal to k times a squared. K is equal to 1. So p squared is equal to a. Oh, sorry, it's a cubed. Oh my gosh. Okay. So what is p squared? So p squared is equal to a. What is a again? Oh, a is the astronomical units. Okay, so I need to get first the semi-major axis of... Oh my gosh, okay. So let's first get the semi-major axis of this Hohmann transfer orbit right here, right? And in order to do that, what we just gotta do is... Okay, let me just cut that. Yeah, so the semi-major axis of this orbit, right? This Hohmann transfer orbit is calculated by getting the periapsis and the apoapsis and summing them together and dividing them by 2. So basically averaging them. So what is the periapsis? Well, it's 12.45. Well, no. 0.92 Kerbin units plus 1 Kerbin unit divided 2. Yeah, so this is... Let me just get a calculator. I mean, I could just do this in my head, but come on. 1.92 divided 2 is 0.96. 0.96 Kerbin units. So that's the semi-major axis of this Hohmann transfer orbit. Right. So now, can finally put this back. So p squared is equal to a cubed. What is a? The semi-major axis of the Hohmann transfer orbit, which is 0.96 Kerbin units, and then cube that, and then let me just calculate that. So that's 0.96 cubed. So that is 0.884736. I could probably just round it. And then, so that means p, so the period in Kerbin years of this Hohmann transfer orbit is square root of 88.88. which is equal to, what is that? 0.88 to the power of 1/2. That is equal to 0.93. Okay, let's just 938. Well, okay, let's just round it up to 0.94. So 0.94 Kerbal units. So that is the period of this Hohmann transfer orbit, right? So, I guess let's continue. So yeah. Okay, so they converted to Earth days. Okay, so what I basically need to do now is to convert it to Earth years. I mean, convert this period of, okay, no, this is not, oh my gosh. No, 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 I did it incorrect. I did this incorrectly. Well, not really. Let me just delete that. Bro, what? Fill this with white. Let me just get rid of that. You guys don't mind me. I'm just, what is this? How, it's not a fill bucket? Okay, there you go. Okay, let's just put Kerbal years. Kerbal years. KY. Okay, so now I guess we'll just convert it to Kerbal days. How many years are there in a Kerbal day? I mean, Kerbal days in a Kerbal year. I don't know. I should probably Google that. Alright, let me just Google it. Alright, I Googled it and it's apparently, so, okay, 1 Kerbal year is equal to 426 Kerbal days, I think. Wait, let me Google it again. How can I forget that quickly? Well, it's not like I forgot, it's just that yeah, let me just Google it again. Yeah, okay, so one Kerbal year has 426 Kerbal days, right? So if that means a period is equal to, so that means the period of this period has, okay, 0.94 times 426, 400.44 Kerbal days, right? So that is great. So what now? What do I do now? Good question. So so the full period of this Hohmann transfer orbit is 400.44 Kerbal days. Wait, that means that the half, I'll just do period over 2 is equal to 200.22 Kerbal days. Wait, is that correct? I think so. 400.44, yeah. Oh my goodness, why do I need my calculator? Okay, like, what? I should be doing mental math. Okay, so the full period of this Hohmann transfer orbit is 400.44 days. Travel to Bill Kerman encompasses half of one orbit, so approximately 200.22 Kerbal days. Right. So using the daily motions of Earth and Mars, using the daily motions of Kerbal and Bill Kerman, compute the ideal relative position of Kerbal and Bill Kerman during launch. Okay. So alright, so basically Mars, okay, yeah, Mars completes one revolution around the sun, 360 degrees, in 687 days. Earth days, I think? Yeah. So that means it moves 0.524 degrees per day. Okay, in 259 days. Okay, so now, first, I need to calculate how many, wait, what? Okay, so first of all, what I need to do is to calculate, how long it takes in Kerbal days for Bill Kerman to go around the sun, right? So first I need to calculate his orbital period or something. Like, are you serious? Like, okay. Does it say it in the game? Wait, let me check. Wait, let me check first. Okay, Bill Kerman. Like, bro. Okay, hello, Bill Kerman. Bill Kerman is strangely happy. Okay, oh, there's no orbital. Ah, shoot. Okay, what is this? This is, there you go. Okay, so now, I just need to get, a little bit past the apoapsis. Right? Here we go. And then how much time does it take? Wait, no, I already have the... Wait, what? Wait, what am I even calculating? Wait, what? Oh, I'm trying to calculate, Bob's, stuff. Wait, no, I can just calculate the Kerbal year. Okay, but here it says 384 days and 3 hours. So that's 384 and a half. Okay, so let me just put that here. So the period of Bob's orbit, Bill Kerman's orbit is 384.5 Kerbal days, because there are 6 hours in a Kerbal day, I think. Are there? Okay, let me just check. Yeah, I'm correct. So a Kerbal day has 6 hours. Yeah, 6 Kerbal hours. Well, yeah. So yeah, so the orbital period of Bill Kerman is 384.5 Kerbal days. So if we go back to the math, yeah, so yeah. So what do we need to do now? Oh, yes. We're supposed to complete it. So Mars completes 1 revolution around the sun. Okay, let me just replace this with Bill Kerman. So Bill Kerman completes 1 revolution around the sun in 384.5 Kerbal days. So that means, okay, so I just need to do 360 degrees. 360 degrees divide 384.5 Kerbal days, which is equal to, let me just, wait, am I doing this correctly? 687. Oh, okay, yeah, yeah, so 360 degrees divide 384.5, yeah, is equal to, alright, 0.93694 degrees per Kerbal day, right? Right. So that means I just need to okay. So now what's the next step? So Bill Kerman completes 1 revolution around the sun, 360 degrees in 384.5 Kerbal days. So that means it moves 0.94 degrees per Kerbal day, right? Okay. So in how many days? So 200.22 Kerbal days. Okay, let's do that. So that means, okay, so in 259, I mean, in 200.22 Kerbal days, Bill Kerman will have moved X degrees, right? So let's do 0.94 times 200.22, and then we get, what do we get? 0.94 times 200.22. We get 188.2068. So let's just round it up to 21. So 188.21 days. Kerbin days. Wait, no, that's degrees, right? Wait, what? Okay, no, I multiplied by the degrees, so I mean by days, so I get degrees. Right, right. So, B moved, moves. Well, let's just do some symbolism. 1 point. I don't know what I'm doing. 188.21 degrees, per 200.22 Kerbin days. Right. So what does that mean? That means then that at the time of our launch, Bill should be 188.21 degrees ahead of Kerbin. Right? I think that's what it means. Did I do the calculations correctly? So okay, so that means that theoretically then, assuming my math is correct, when I launch, right? Bill Kerman should be about here or something, right? So if this is where Kerbin is, then Bill Kerman should be here. Why is this right clicked? Oh my gosh, what? Okay. Yeah. So Bill Kerman should be about here. Wait, let me get my protractor. Protractor. Alright. So this is my protractor. Yeah, you guys can't see it, obviously. But, yeah, so if I do this, let me see here. So 8 degrees is about here. Alright, so Bill Kerman should be about here. This is where Bill Kerman should be, right? Because it's 180 degrees, so circle like, a semicircle. Yeah, a semicircle like this way. And then plus 8 more degrees, which means Bill Kerman should be about here, right? So I think I should probably just time warp to that time. I think. Yeah. Let me just time warp to here. Warp here. Yeah. And then I'm gonna make a quick save, right? Because I could just be wrong. My math could just be wrong, or we could have a mistake. So, oh wait, no. Wait, let me stop. Here. To calculate the position of, oh, okay. To calculate the position of, say, of Bill Kerman at the time of launch, subtract the amount of its motion during the spacecraft's travel time, which is 200. Wait, oh wait, no. Okay, no, the amount of its motion, right? Of the motion of Bill Kerman, which would be 200. Wait, would be 188.21 degrees, right? From its point of arrival, 180 degrees. Okay. So that means then that, okay, so the launch window, so transfer window is equal to the, okay, 180 degrees minus 188.21. Right. It's equal to negative 8.21 degrees. So in reality, right, Bill Kerman should be negative 8.21 degrees, which is about 8 degrees, right? 8.21 degrees behind Kerbin. Oh, okay. I remember now. I remember. Well, yeah, because this is my like second or third attempt. This is my like, yeah, I remember, because this is my third attempt, kind of, uh, of recording this episode. All right, so that means negative 8.21 degrees, which means Bill should actually be. Let me just use my protractor here. Right. Wait. So this is 10, 20. Okay, right here. Right. Bill should be in this at this green dot. I don't know if you can see that. I don't know if YouTube's gonna be able to show you that. um, I don't know if you're able to see that, but this is where Bill Kerman should be relative to Kerbin, right? Relative to Kerbin's orbit around the sun or around Kerbal. Yeah. So this is where Bill should be. Yeah. All right. I saved the image just in case I delete it or something. I don't know. So yeah, I guess we'll just start time warping. Um, and yeah. Well, this is gonna take a long time. Like, I mean, to just time warp, right? Hmm. Okay then. Well, I guess I'll just let it time warp in the background. All right, let's do this. So now, what do I need to do? What I need to do now is to I guess I should first build a rocket or something. I have one rocket here. Okay, where is it? So rocket N, I think. I think this has a lot of delta V. Okay, so now let's do this. Alright, so let's launch this right here. I gotta be a bit faster now because I have to go soon. So right. So now, first of all, I need to set Bill Kerman as my target. Okay, let's do this. 3, 2, 1. And liftoff. Okay. This is kind of loud for you guys, so I'm just gonna make it quieter. Alright. Right, so now, just gonna start our gravity turn. Okay, our thrust weight ratio is kind of big. Here you go. Ooh, amazing separation. Alright, so now I just need to make sure that the periapsis is going up as well. Wait, did I do that? There you go. Separated. Alright. 3, 2, 1, 0. There we go. Alright, so this is a circular enough orbit, right? So now I just gotta add a maneuver. Yeah. And then we'll be on our merry way. Alright, okay, that's probably close enough. Okay, let me just point to the thing. 0. Right, here we go. Three, two, 1, 0. Alright, let me check the encounter. Okay, that's actually pretty good. Alright, let me just save game. I kind of forgot to open the solar panels and the communitron. There you go. So if I go say, yeah, do a 90-degree angle. Alright, that's probably the closest I can do. So what I need to do is to make this more trustable, I'm gonna decrease the thrust limiter. Alright, let's do this. So I'm just time warping. 4, 3, 2, 1, 0. Alright, and then I'm just gonna put it in 4 times physics warp. No. Okay, that's close enough. Come on, okay. So now I guess I'll just... Okay. Okay, this thing needs less thrust. Alright, that's close enough to the actual encounter. Alright, let's do this. So, okay, so we're gonna do the encounter. So now what I need to do is just warp here. I have full thrust. I'm just gonna cancel the relative velocity. Alright. My speed relative to my target is almost fully cancelled. 3, 2, 1. Okay, there you go. Now it's cancelled. Now I just need to point at the target and then just alright. So now I just need to time warp. Alright. Wait, let me just... Alright, now I'm just gonna go point at the target. Oh my gosh. Okay, let's not use physics warp. Right? Yeah, so this is the moment. I'm just gonna save game. Alright. Then I'm gonna... Hey, Bill Kerman. Alright, let's go this way. Oh no, cause it's... Bruh. Okay, that... Cause it's pointing at me. Okay. Let me just go this way. Yeah, okay, this is probably good enough for the thumbnail. I mean, I can always just quick save back. You know, for a better thumbnail. Okay, but yeah. So, just get inside here. Your crew. Okay, I'm gonna transfer Jebediah to this command module. Then I'm gonna go here. Boom! Bill Kerman, Bob Kerman, and Jebediah Kerman are reunited. Okay, and then there. Okay, now I just need to time warp. Alright. Here we are. Oh, I guess I just gotta burn this. I'm gonna do the physics time warp. 4, 4, 3, 2, 1, 0. There you go. Okay. So, add maneuver. I guess I just gotta increase the orbit until we get a close enough encounter. Oh, I guess I gotta reduce it. Oh, there you go. Ah, okay. Okay, this is better. This is way better. Alright. I guess I just got a time warp. Okay, so that took a bit longer than I expected, but now we're basically on a, I guess, trajectory to getting an encounter with Kerbal. Right, so, if I just... Ready to point. Okay, I'm just gonna do half throttle. Alright, so now I just need to do radial out. There's the blue planet. It would be really cool. Oh my gosh. Okay, never mind. There you go. Then I'm just gonna toggle the solar panels, I guess. Okay. Okay, let's do this. Oh, no, no. Okay. Alright, let's do this. Boom. Alright. Let's do service. Alright. Look at that beautiful sunrise. So we're landing in this kind of mountainous region and all that. There you go. We are safe at last. Jebediah, Bill Kerman, and Bob Kerman. We have touched down. Let's go. Photo thing. Alright. That's pretty cool. Right. Plant flag. Alright. Okay, Rocket N has successfully landed. There you go. Let's take another picture. Amazing. Take surface sample? Okay, this is probably... Wait, so what if I do an EVA report while flying? Yeah, flying over Kerbal Mountains. If I did a crew report... Yes. Whoops. Bro. This is the wrong button. Oh my gosh. F grab. Board. I'm just gonna take surface sample. Then EVA report. Board. And then yeah, let's do this. Recover vessel. Hey, okay. So we got some science. Oh, that's a lot of science. Oh wait, no, it's just 52.8. Okay. Well, we did it. We rescued our Kerbals. But yeah, I guess that's today's episode. Thank you so much for watching, and I hope you subscribe if you're actually interested in this type of content. If you're not, then don't subscribe, okay? I want to have loyal subscribers. Alright. Bye everyone. And have a good day. Or night.